So just thought I'd do that. That saves us a couple minutes later on here as the numbers climb. And it's 7 o'clock, and we'll get started because I'm not the meat and potatoes of the act anyway tonight. I just wanted to welcome everyone. My name's Lori Borthwick. I'm the Bay of Quinte Green Party of Ontario president, and we're really excited to be hosting this speaker series on COVID-19 vaccines and variants with Dr. Gerald Evans and Dr. Alan Bernstein, and our host, John Hirsch. It's going to be a really an interesting night and lots of really good information. I would also like to take a moment to recognize that I am an uninvited settler here and here in the Bay of Quinte. I'm on the traditional territories of the Haudenosaunee, the Anishinaabe, and the Huron-Wendat people, and that along with the amazing blessing of living in such a beautiful area, there's also, I feel, a responsibility to try to ensure that we protect and care for the land in a way that allows life to go on for many generations here. So I just like to always start with a little bit of thoughts about the lands on which we live. And someone else who's spent a lot of time caring for the land on which they live is our host tonight, John Hirsch. He came to the Picton area in 2014, and he immediately got involved doing many projects that to protect the South Shore, one amongst many. There's quite a list. And in 2018, he was convinced to represent the Ward 9 in South Marysburg, which he did. And so what makes him the perfect host for tonight is that he has spent every day since the pandemic has been announced, I guess, updating 300 families, over 300 families in his Ward 9 daily of what's going on with the pandemic and what's next to come. So I just think that that is amazing, and that makes you know, he's been keeping right up to date on all the science and all the developments. So that makes him a terrific host for us this evening. And so without further ado, I will pass this over to you, John. Thanks so much.
Thank you very much, Lori. Yes, as you mentioned, I have been sending out a daily email with updates on the number of COVID cases, progress on the vaccines, basically curating trusted media sources to constituents and in essence, anyone who asks. Ever since this day in 2020, I just realized today is the 1-year anniversary of my daily email. I find there's a real hunger for accurate information about the pandemic, so I've been trying to fill that need. My list started with 35 email addresses a year ago. It now reaches 190 email addresses and over 300 families. So hopefully that's of value to the people. I certainly get comments every week. If you want to be added to that list, it's absolutely free of charge. And you just need to send me an email at jhirsch@pecounty.on.ca. And of course, you can find that email address on the county's website where all the councillors are listed. But enough about me. Normally, I don't really look forward to hosting events like this, but this one is very different. It is exceptionally different. We have two exceptionally talented, accomplished, and personable experts to talk about today's most timely subjects, vaccines and the infection-related aspects of the virus. And most importantly, to answer your questions. So I'm delighted to present Dr. Alan Bernstein, who is a member of Canada's the federal COVID-19 Vaccine Task Force, President and CEO of CFAR, which is a Canadian Institute for Advanced Research, a global research organization. Alan is a member of the Order of Canada and has spent a career in virus and vaccine research. He and his wife live at least part of the year in beautiful Prince Edward County. He'll make some opening comments about Canada's vaccines and will join Dr. Evans later for question and answer. Dr. Gerald Evans is the Medical Director of Infection Prevention and Control at Kingston Health Sciences. He's a member of the Ontario Science Table, Chair of Infectious Diseases at Kingston Health Sciences Centre and Providence Care Hospital, Affiliate Scientist at the Institute for Clinical Evaluation Sciences at Queen's University, and Editor-in-Chief of the Journal of the Association of Microbiology and Infectious Diseases Canada. Dr. Evans will give a presentation on the infection-related aspects of COVID-19 and how it has been dealt with from a public health and safety perspective. And both of these esteemed folks will be pleased to answer your questions as we enter, hopefully, the final stretch in dealing with the pandemic. So how this will work is this, as Lori mentioned, while our experts are making their remarks, you, the audience, will be formulating tough questions for them to answer. And I would ask that you type your questions into the chat box feature in Zoom, not the Q&A box. The Q&A box actually doesn't work as well as the chat function. Chat function is better. So I'd appreciate if you do that. Once they've finished speaking, I will then relay the questions, sort of assimilate them, and get some responses. So I guess without further ado, I believe there's a slide deck coming, Dr. Evans, and Dr. Bernstein's going to start off.
Okay, well, thank you very much, John. It's really a great pleasure for me to speak to you this evening. I'm going to talk really short. My talk will be very brief because I want to hear Dr. Evans, first of all, and also I want to leave time for lots of questions and hopefully some answers from Gerald and I to your questions. And I want to thank John and the Green Party for hosting and Green Party for organizing all of this, and Don Wilford for making it all happen from my point of view. So I'm going to show just a couple of slides, sort of a vignette of some aspects of vaccines, just to kind of get your juices flowing and to set the context for what Dr. Evans is going to talk about. So maybe, Dr. Evans, the next slide, please. We can go right to the next slide. This is taken from a WHO picture from about a week ago, and it shows in different colors the number of people who have both number of confirmed cases. You'll see that it's been worldwide over 120 million cases, well over 120 million cases in the world over the last year. It's quite a remarkable figure. And of those 120 million, close to 3 million people have died. Again, quite a striking figure. I think the other figure that's also quite striking is, as of a week ago, there was 238 vaccines administered around the world. And those vaccines have been mostly administered in North America, of course, and in Western Europe, not really around the world, which is a problem. That number of 363 is probably now closer to over 400 million doses. It's a remarkable number to think that in a year, we not only have vaccines in 1 year, but we also have 400 million people already vaccinated. Next slide, Gerald. So what is a vaccine? How do they work? Well, just so we're all on the same page, this is a definition I took from the WHO, the World Health Organization website. Vaccines are, of course, designed to reduce the risk of infection and also transmission of the virus or bacteria by training our immune system. It trains our immune system to recognize and to forearm it to fight any incoming pathogen, such as a virus, such as SARS-CoV-2 or COVID-19, or some bacteria. The best vaccines, of course, are safe. They safely will deliver what's called an immunogen, which is a specific type of antigen. Now, antigen just means it's what your immune system recognizes as being foreign. And because it's recognized as foreign, it makes an immune response. And the immune response typically is antibodies, but not only antibodies, but we won't get into that this evening. And that trains the immune system to recognize that pathogen and to kill it or to neutralize it in some way. And so vaccines are, the history of vaccines go back almost 200 years now, when Edward Jenner discovered that milkmaids in England didn't get smallpox. And the reason they didn't get smallpox was that they were milking cows. And because they were milking cows, they were exposed to the cowpox virus, which was basically serving as a vaccine, because the cowpox virus and the human smallpox virus are very similar. And so they were effectively being immunized against smallpox. That's why vaccines, if you know your Latin, vash comes from cow. And that's the origin of the word vaccine, is from these milkmaids who were milking cows back in the 1700s. Now, smallpox historically has been the world's largest killer of humanity. Hundreds of millions of people have died of smallpox. This year, nobody will die of smallpox. Last year, nobody died of smallpox. And next year, I guarantee you, nobody will die of smallpox. And the reason is smallpox has been eradicated because we have very effective vaccines that have eliminated, or eradicated is the technical word, eradicated smallpox from the planet. So that's how powerful vaccines are in defending humanity against this age-old battle with pathogens that we're surrounded by. Next slide, Gerald. Okay, so this is basically what a vaccine does. So here's the coronavirus. This picture I'm sure you've seen 100 times. I show the slide because I'm quite proud of it. I actually put this slide together. I'm not good at making slides, but I did this one. So you have to, applaud it and say, oh, this is a great slide, Alan. There's the coronavirus, and those red things on there are the spikes. They're the spike proteins, and they're the things that in one way or the other serve as the immunogens, the antigens that are recognized by our immune system and fight the immune system and fight off the virus. So thank you, Claudette, for recognizing it as an excellent slide. I got it in the chat room. That's excellent. Okay, so the next slide. Now, well, let's back up for one moment. In the old days being in the 50s, before we had all these newer technologies, most vaccines were either chemically inactivated forms of that virus. So the polio vaccine, going back to the 50s, was a chemically inactivated form of the polio virus, and whatever virus you want. Or it was a virus that was so-called attenuated. It was not as infectious as the normal virus, and so our immune system could deal with it. Today, we use much more sophisticated and safer techniques than using whole viruses. We actually can use recombinant DNA technology to clone the gene for that spike protein, that red protein, so that you're never exposed to the whole virus. You're in no danger of actually getting that disease, of getting COVID-19 by being vaccinated. Whereas in the 50s, there were some children who got polio, for example, because the batch of polio virus had not been completely inactivated back in the 50s in a US batch. And ironically, it was vaccines made here in Canada at the old Connaught Labs north of Toronto that was then shipped to the United States as a goodwill favor. So we should remember that when, out of the generosity of their heart, the Americans loaned us 1.5 million doses of the AstraZeneca vaccine. But we can come back to that if you'd like. All right, next slide. Okay, now you've heard about variants. These variants are mutants of the sort of corona classic, if you will, the coronavirus classic. And these mutations are simply, if you think of a book, they're really a mistake that's made when the virus replicates. And all living things make mistakes when they replicate. That's how evolution works. And so this is a particular mutation. You'll see on the top line, the original, you'll see GAA. That codes for an amino acid in the protein of the spike gene called glutamic acid or glutamate, and it's abbreviated E. And then there's a mutation that goes from the G to an A, and then instead of having a glutamic acid, you get a lysine, which is abbreviated with a K in that position. So the mutation, the code for it is E484K. The E is a short form for glutamic acid. I'm telling you this so now when you read the scientific papers, you'll understand the nomenclature, or even in the newspapers now. 484 is the position in the spike protein where that mutation took place. K is now, it becomes a lysine instead of a glutamic acid. This is a very bad mutation. This is the South African mutation. And the reason it's bad is because it's a so-called immune escape variant. These viruses, this particular variant is a variant of concern, as it's called, is about 5-fold less sensitive to the antibodies that are normal of the current generation of vaccines make, and we can come back to that. Next slide, Gerald. So this is what the same thing looks like, though, in 3 dimensions. This is actually a picture of the spike protein. It's an actual diagram from X-ray crystallography of the spike protein. And the spike protein actually forms a trimer. There's actually 3 spike proteins that come together and to form the shape of that little red thing you see in the pictures of the coronavirus. And you'll see the E484 at the top there, on the top sort of the right there, and you'll see it down near the bottom, and you'll see it on the left side, on the sort of, it's north, south, east, west. You'll see it the north and the south and the west aspects of this protein. That's the E484 mutation. The other variant that we hear a lot about, because it's actually taken over here in Ontario, and certainly took over in the UK very quickly, is the UK variant, which is affectionately called B117. And it's N501Y mutation. So you now know that it's in position 501 of the spike protein, and that's where it sits in the protein. And the result of that is it changes the shape of that protein. So it's no longer recognized by the antibodies that are elicited when we're immunized by any one of the vaccines that are used at the moment. Now we'll get into it if you want, but there are new vaccines being made now that take into account these mutations, and we can talk about that later. Okay, next slide, Gerald. Okay, so this is now an interesting graph, and it's actually better if it's shown as a video, but I couldn't do it, so we're going to look at one point in time, which is basically today. And on the horizontal axis, on the x-axis, is the number of doses that have been given per 100 residents in different countries. And on the y-axis, the vertical axis, is the deaths per 100,000 people in that country. And lots of people tell me, they complain to me about how badly Canada is doing in the rollout. And I always say, it's not the complete picture. The complete picture is not how many vaccines we've got. The complete picture is including how many people have gotten sick or died in that country. So if you look at the US and the UK up in the upper right there, in those blue dots, you'll see that the blue is for advanced economies, red is the developing world. You'll see that the US has gotten a lot of vaccines. That's why the size of the circle is proportional to how many vaccines it's got. And it's up to, and when this photograph was taken on March the 17th, somewhere around 35 doses per 100 residents. So about a third of Americans have been vaccinated with at least 1 dose. But you'll also see that it almost wins the race in terms of how many people have died from COVID-19. On the y-axis, it's about 170 deaths per 100,000 people. And the UK is even worse. It's a little higher for deaths and a little bit better in terms of how many vaccines have been administered. And then if you go towards the left, you'll see that in Canada, I put an arrow at the smaller blue dot. That's 8.9 doses of vaccines per 100. So that number today it's a week later, that number today is about 11 doses per 100 residents. But we're also a lot lower in terms of number of deaths. We're down around 60. So we're about 3-fold lower per 100,000 individuals or per person compared to the US, and about almost 4-fold lower, not quite 4-fold lower than the UK. So the complete picture is not that we've gotten a lot fewer vaccines. The complete picture is we've gotten a lot fewer vaccines, but we also have a lot fewer cases and a lot fewer deaths. So that to me is the complete picture. I'm not making excuses that we don't have more vaccines, but to me, this is a more complete picture. Now, I think that may be the last slide I have, Gerald. Let's just see. Yeah, it is the last slide. So that's been a very quick, high-level tour. We'll get into a lot more as we talk at the Q's and A's, but I'm going to sit back now and listen to Dr. Evans speak.
I had to unmute myself and I briefly forgot how to do it. So I'm going to go back here now to the slide set. That's great. A very nice overview, Alan, on things. So let me go back into slide view with this. And let me back up to my first, oh, there's my first slide. So really, I was going to kind of initially had thought about doing a talk that envisaged the last year. And if you guys ever want me to drive you crazy, I can come back and do a talk about which I entitled Of Zoonoses, Zombies, Zeitgeist, and Zoom, which is just a masterful alliteration using the letter Z. But what we're going to talk about tonight, I'm going to continue on with the subject that Dr. Bernstein's really got us into, which is the issue of vaccines. And of course, what is now really the flavor of this first third of the year, which is the rise of variants. Just to remember, January 30th last year, that was when it was declared a public health emergency of international concern. In March 11th, it was declared a pandemic. And as Dr. Bernstein commented on, we've come a long way, baby, since that happened. We've got vaccines now, and not only have we got vaccines into a third of a billion people on the planet. So what I'm going to talk about very sort of quickly in the next I'm hoping about 15, 20 minutes is to go where we are right now, talk about variants, and then talk about sort of vaccines in general, and then where that relationship lies with variants of SARS-CoV-2. So this is really very up to date. This is Southeastern Ontario active cases of COVID-19. You can see going back to November, we saw this rise in the late fall into December, where we had the second wave here in the southeastern part of Ontario, a little bit of a blip after the holidays into the sort of late part of December and January. And then we had this beautiful decline, and now we've seen this big jump, and it's actually higher than the second wave when you look at active cases, prevalent cases here in the southeast. And that's really being driven by variants. And I put in here B117 because B117 is the variant that we're seeing most frequently right now in Ontario, and less so some of the other variants of concern that Dr. Bernstein mentioned. So yeah, we're well into a third wave, and it's being driven by variants. What did the variants do? Well, what they did is they drove up the effective reproduction number here in the province of Ontario. The red line is a RO, reproductive number of 1. Anything below that is good. Anything above that is bad. You can see what happened way back in the first wave back in the spring. It did drop down, but eventually only after we went into lockdown here in Ontario, right after the holidays, and it took a few weeks for that to happen. But then we had this beautiful drop down to almost 0.8. It would have been nice to be about 0.7, but that's a whole other thing I can discuss with you. But essentially after that, the variants which had been introduced pretty well back here began to emerge. And then, of course, around the early part of February, we started reducing some of the measures of public health. And that's where Canada has been most effective. We've had a really good public health response, which the Americans didn't have. And I think that's what reflected somewhat in the numbers that Dr. Bernstein shared with us in terms of deaths. The Americans have had over 500,000 deaths, and that's because they really didn't pay a lot of attention to public health. They had some ideological things which got in the way. So here we are as of, I guess, yesterday. What's the date today? Today's the 24th, so that's yesterday. This is one of the few subjects I've lectured on over the last 30 years where I have data literally up to today. So basically here in Ontario, most of the variants that we have been able to distinguish, we haven't got them all, are mostly B117. They're 93.4% of all the variant cases that have been tested by whole genome sequencing. In other words, we've actually laid out the code of the RNA of the virus. Just remember that we found the mutation mostly because we look for that N501Y mutation, which is common to most of the variants, including B117, the South African and Brazilian one, because it's a convergent mutation. But we still are waiting to sequence about 14,000 isolates, RNA positives, to determine what the spread is, but it's certainly looking in favor right now of B117. I'll put this up here because this is not something I'm really proud of here in KFLA, but if you look at the percentage of positive cases that are now variants because we can find this N501Y mutation in positive samples, it's at 60% for KFLA. Where you are in Hastings, Prince Edward County, it's down at 8.3%. And actually to the west, where you guys are in HPE, actually you're doing very well in terms of sheer numbers. And that's probably because you don't have a lot of variants. We unfortunately have a lot of variants, and we have a lot of socializing university students. If you'll all recall your days of youth, when you were between ages about 18 to 24, that's when you're socializing the most and allow transmission to occur. And this is all being driven because we know these variants are more transmissible. This is the reproductive number of the variants that are of concern we're seeing in Ontario. Again, chiefly B117. You can see they're all well above 1. These are the colored zones the province uses. If we were dealing with the old original SARS-CoV-2, the Wuhan strain as we call it, they're well below 1. So these new variants are more transmissible for sure. And that's reflected in when you look at rates of infections. Here's what our life would look like right now if we were just dealing with the early variants that were present in Ontario. We'd be really heading down here towards the general concept of a yellow zone or an orange zone in the province. But the variants are stopping that from happening because they're driving up numbers. These are the same timescales here. This is out to early March. This is data from the science table here in Ontario that I sit on. We're no different than anybody else in the world. One of the things that we really need to learn about this virus is if things that happen in other countries tend to happen in your country or your jurisdiction. And this is just showing you what's happened in some of the representative countries of Europe and then the UK, which is no longer part of Europe, thanks to their political decisions. But you can see the Ontario numbers, which are reflected in these gray blocks, are really mimicking exactly what we've seen in these other countries. When the variants of concern arise and begin to predominate in a jurisdiction, they will generate cases going up, and that's where we are now, and that's what's causing the third wave. These are some modeling projections that the science table has released. We've looked at in scenarios where the variants are spreading in a fairly low manner to a medium to a high manner. And you can see here, these are projections out to early April. Case numbers are going to climb significantly. And so we have to do everything we can to control them. And controlling variants right now is principally public health measures and maintaining those. But I'm going to show you in a second that vaccines actually have an impact, especially B117, which is the predominant variant right now. There's actually pretty good data that our current vaccines work against that variant. But as Dr. Bernstein mentioned, of course, we have lots of ability to quickly change vaccines using new technology to adapt to other variants that are popping up. So let's talk about the variants fairly quickly here. Dr. Bernstein took away my flourish here. What generates variants of SARS-CoV-2? Well, viruses, just like people, make mistakes. And he's absolutely right. That is the driving force of evolution, which is no longer, by the way, a theory. It's actually the law of natural selection that drives evolution. People still call it a theory. It was a theory back in the late 19th century, but we've pretty well proven that it's true now. So when anything replicates, and viruses are things that replicate, they can cause mistakes to happen. And that mistake happens because the enzymes that drive that replication of RNA and DNA, called RNA and DNA polymerase, actually make mistakes all the time. Not a lot, but they do. And just to sort of show you that we've actually studied this in the past. And this is SARS-CoV-2. It's a single-stranded positive RNA virus. It has a frequency of mutation somewhere between about 10 to the 4 to 10 to the 6 replications. And so one of the ways you stop this from happening is don't let the virus replicate. If the virus doesn't replicate, it can't make mistakes. And one of the mistakes we've made is we've allowed this virus to replicate like crazy. And if you imagine tens of hundreds of thousands of viral replication cycles in an infected person, and you look at the numbers that Dr. Bernstein showed you of infected people that we documented of over 120 million around the planet, this has given the virus a big chance to really produce a mutation that is going to eventually result in something we call antigenic drift and the production of new viruses. And so this is the mutation rate. It's also dependent on genomic size, which I won't go into now, but this basically sits in this middling group, SARS-CoV-2. The other thing we know and people have studied now recently is where do these mutations occur in the virus? Because the virus makes lots of proteins and they have regions in their genetic structure which mutations occur. And what's fascinating is R5 that's the one that codes for the spike protein. And it's the second most frequent place that the virus tends to develop mutations in. So it's not surprising that we're seeing mutations in spike protein that are generating these variants. The variant thing is really fascinating. And one person asked me once in a talk, well, how do you come up with all these names and everything? So the evolution and you know, this is from a paper that was published in Nature Microbiology recently that sort of talks about how we called them. Here's the original sort of Wuhan strain. It's basically evolved, and you get these pictures, these sort of dendritic diagrams, which show you the thing. And people always say, well, that looks very confusing. So let me make it less confusing for you if you're into genealogy. You just got to turn that thing 90 degrees, and then you get the family tree of SARS-CoV-2. So here it is originating, and then these mutations occur with replication. In humans, we do that by joining together two individuals who share different genetic material, which creates this. And so you get basically sons and daughters and grandsons and granddaughters. And here we are now out in the B1 range when we started out in A. So basically that's, if you can understand genealogy, you can understand viruses and how they basically evolve into different variants. Why are we concerned about variants? Well, we're concerned really because three major things can happen with variants of SARS-CoV-2. These variants, because they're occurring in spike protein, may increase transmissibility. This is the attachment point that the virus uses to infect you. It may increase the virulence of the virus, make it nastier, more deadly. And as Dr. Bernstein's already commented on, it may decrease the protection from current vaccines, or if in fact you've had a previous natural infection with the original virus, it could be causing some problems that the immunity you develop to that initial infection or to the vaccine you're administered somehow is not going to work against these variants. So these are the variants that have been described. There's B117, the one that arose in UK, B1351 in South Africa. They've got all these fancy names. By the way, the Americans, with their unopposed replication of virus, have done a majorly good job of now producing variants, one called California, one in New York. There's also one in the Midwest, which we're beginning to be concerned about because they do represent potentially immune escape. These are the kinds of mutations which we've already been introduced to with the nomenclature. What's common about them is the N501Y, which we do typically associate with B117, is in fact seen in these other variants, including the one from South Africa, the one from Brazil. And that's how we can spot them with our current testing, because we can look for that mutation. When we detect it, we know it's a variant. Then we have to go to whole genome sequencing to figure out which variant it is, and that's what takes a little bit longer. Here's the South African variant, which Dr. Bernstein made a comment to, and you can see right next to the N501Y that I've circled here, you have E484K. So that's really essentially where it is, and we are getting really good at detecting them because we got that N501Y probe that we can use on positive specimens. So schematically, this is what the virus looks like. Here's the original wild type or Wuhan or original strain of SARS-CoV-2. Here's B117, and you can see here that there are mutations that have occurred in specific parts. So the genome is represented here by this circular structure, and this part here is the spike protein, and you can see there's actually quite a few mutations here. Again, that's the R5 district. This is the R6 over here. And so when these mutations pop up, they're very relevant when they appear in the spike protein. When we zoom in on the spike protein, what we find is that N501Y is the most common mutation. It does relate to the ability of the virus to attach to the ACE2 receptor, which is the receptor you have in your body on the respiratory epithelium, which allows the virus to attach and infect you. We think that this is primarily what's driving this increased transmissibility, but I'm going to show you some other things in a couple of slides that also explain it. There's all these other mutations too, which are interesting, but I'm not going to talk about them because we could get into a lot of earnest discussion. But anybody other than Dr. Bernstein, who's a basic scientist, I'm happy to discuss it with you because it is fascinating, some of these things. So the mutations in the spike protein, why are they important? They're important because, again, it's the viral receptor that allows the virus to infect you. And our current vaccine strategy, as Dr. Bernstein explained, is actually to make antibodies against spike protein. So if you want to imagine the spike protein as a Lego block, here it is here. And so if we examine what's happening when we get mutations, Here's original SARS-CoV-2. Here it's attaching to your cell, which has a somewhat complementary Lego block that allows it to attach. And here's antibodies that the vaccine's made or a natural infection's made that block that receptor. In the variants, though, the receptor, that spike protein is now changed from one with one little connecting piece, so you have to remember your Lego stuff, to one that has two. Well, what's interesting about one that has two Lego blocks is it even fits this ACE2 receptor better than the original spike protein. And again, when we make antibodies, they block some of it, but not all of it, because they can only attach to one part of it. So it's a nice schematic way of looking at how that spike protein changes and how it impacts binding an infection, and how it could create problems with immune escape if the antibodies can't neutralize it. The other reason we're concerned about variants is, man, these babies spread fast. Air travel, despite being markedly reduced during the pandemic, continues on. And I just actually draw your attention to this little diagram in the lower section here, because this represents the sort of 10 groups of major variant changes that have occurred in SARS-CoV-2. Here's the original strain, the 19A, and you can see this evolution over time. We got D614G, which came in, and actually by the time Kingston and Southeastern Ontario started seeing cases, we already had that mutation in there. It wasn't an important mutation, didn't create many problems, but it certainly predominated. And now we're seeing these other variants popping up, which are represented in these orangey yellow colors. And as you can see, they're starting to come up, and they're going to replace these other guys, because as Darwin said, if you're more fit for some reason in the ecological niche which you occupy, you will begin to predominate, and the nature will wipe out the other things. Just to show you how bad it is, this I actually took from one of my colleagues in Alberta who just posted it today. This is just a little schematic to show you. In Alberta, they had a case of a SARS-CoV-2 variant B117 imported by an international traveler to Alberta on January 1st, New Year's Day. That actually led very quickly to 42 cases. And now Alberta, although they're not all derived from here, I will tell you that other people probably brought them into the province, is now up to at least 1,886 cases with the variant. And that's over that short period of time here. You can see of just basically about 2.5 months. And this is how it transmits. It goes really, really fast. So let's talk about the transmission issue. We first got a hint of this from the Brits. When B117 arose, it arose in the southeast part of England. And when they looked at the effective reproductive number of what were called SG target failures, or S minuses, we could see that they quickly had a reproductive number, as demonstrated here in the y-axis, that was much higher than viruses from other regions, which were probably principally the original virus. So that was a hint that we were looking at increasing transmission, not the least of which is B117 predominates now. Here's another interesting thing about B117. Not only does it bind to that cell receptor well, it also has a completely different spread of viral shedding. The blue you can see here is the original virus, the non-B117. The pinky red is the B117 variant. And what you can see is that, in fact, the period of transmission is a lot longer. This is the days here, actually, than you see with the original virus, which tended to peak early and then disappear. This one starts a little bit later and just goes on for a long time in the clearance phase of the virus. So this virus essentially starts kind of infecting you about around the same time the other one does, a little less so, but goes on a lot longer. And it's why in public health now we're actually considering that we're going to, maintain a 14-day quarantine or a 14-day isolation period. We isolate people that are infected, we quarantine people who are not infected, because this virus is showing that it's got some tricks up its sleeve when it comes to maintaining viral shedding. So what do we know about all of these variants of concern at the moment? Well, we don't know much about the California and New York strains, but the UK variant B117 is at least 40 to 50% more transmissible. 427429, which is the Brazilian variant, is 20% more transmissible. And South Africa looks like it's lining up with the B117 that came out of the UK with being about 50% more transmissible. So that introduces a whole new flavor to what we have to do to prevent transmission. What else happens with these variants? This is very hot new data that we have, some of it generated here in Ontario, but also based on studies from the UK and Denmark, which show, and for those of you who are not familiar with this kind of a sort of forest plot, what we're showing here is the risk increasing beyond 1. And you can see that the risk for hospital admission, ICU admission, and death are much higher with the variants when they're compared with the wild type strain. And Dr. Bernstein would be very familiar with 95% confidence intervals. None of them cross one, and they're fairly tight. So that's probably a reasonable observation. The other thing that's important to remember is that this effect occurs later on in the course of the illness. So early on in the course, they actually kind of look a little bit like the original strain of SARS-CoV-2, but out further, they certainly are generating what seems to be a higher risk. This is ICU admission, and then this is the bad one, this is death. And again, you can see that's driving things up higher. So we're concerned about these variants. They are more transmissible, and they seem to be more virulent, at least potentially more deadly. And so that may have an impact in terms of what we're seeing with young people as well. So the bottom line is, especially for B117, the one that was originally identified in the UK, is that it's dominating the pandemic curve in North America and Europe for sure. It's associated with increased transmission, increased risk of hospitalization, ICU admission, and death. And we have to understand that there's a 10-day time lag. So remember, the variants have been increasing quite significantly now, but there's going to be a lag till we pick up a signal that we're going to see more hospitalizations, for instance, ICU admissions, and of course deaths. And as a physician, that worries me because I work in a hospital, and that means I might be seeing more cases as we get into this third wave. The immune escape phenomenon is fascinating. Everybody knows this story. I actually made this slide up when that story was released back in February, that South Africa said they were going to suspend AstraZeneca. They had a study that showed that it had only 22% efficacy at preventing mild to moderate illness in South Africans. Now they've published that study, and this is what it shows. So it was a double-blind randomized controlled trial in many centers in subjects who were HIV negative. But here's the critical part. They only looked at people under age 65. Remember, almost all of you know that age is the predominating factor that drives severe illness and deaths. So when you're looking at a younger population like this, you're not going to be able to pick that up. And what they actually showed, they had about 1,000 people in both placebo and vaccine recipients, is that in fact, the cumulative events, when you sort of take this to make it a better scale to see at, these are similar graphs. This one just has a different scale than this one, that vaccine and placebo were not statistically significantly different. And that's all fine and dandy, but really with vaccines, especially in our current strategy to avert severe illness and death, this didn't really answer that question. And mild to moderate illness is out there. So what we've also seen is that J&J Janssen, which has just been recently approved here in Canada, also showed a diminishment in its effectiveness. This is real world effectiveness in South Africa when compared to the States, 57% effective in South Africa, 72. But again, looking sort of at moderate severe illness. But Dr. Bernstein and I will both tell you, if you got a vaccine that's 60% effective, you're kind of like, woohoo, this is looking pretty darn good. Novavax as well, same sort of thing. In the UK, 89% effective and 60% in South Africa. This is a very interesting recombinant subunit vaccine, which I think a number of us are very excited about in terms of what it's likely to look at. Just to kind of get a little too sciencey on you here, but this is essentially looking at the Pfizer vaccine versus number of different variants. Here's its effectiveness as measured by a neutralizing antibody titer. This is a measure of the quantity of neutralizing antibodies in the serum of somebody who had received at least a second dose of the Pfizer vaccine. Here it is against the Wuhan strain, very effective. Look at this at 117. It's pretty well exactly the same. So it's going to be effective if you look at neutralizing antibody titers against the B117 variant as it is against the original strain. You look at the Brazilian variant, it's still looking pretty good. It's not statistically that different. Where it starts to lose its problems here is the South African one, where it's statistically less or lower levels of neutralizing antibody titers. But in fact, you could easily argue that titers this high may still be very effective. And of course, they clearly are when we look at some of the data from South Africa. They also, by the way, played around with creating mutant pseudoviruses, which I could really bore you to tears with, by inserting different kinds of mutations in the receptor binding domain. But just ignore those ones because these are kind of like mutant ones that we created. These are the natural ones that have arisen out there in nature. When you look at Moderna, same sort of thing, pretty well same antibody titers here against the original D641G or Wuhan type strain versus B117. When you look at its effectiveness against B1351, yeah, they drop off. The reciprocal infectious dose fifth dose 50 titer that you would get, but those are still pretty effective. So the variants are posing a bit of problem with vaccines, but certainly with the most common one we see here, B117, isn't a thing. What we know then, so we know they're increasingly transmissible, we know they're more virulent. Decreased protection, I think we're going to still wait. We need to get some real world evidence, and some of that's coming out, which actually shows that there may be something more to the vaccine effect than just antibodies. It may be another part of your immune system that's helping you out. So let's briefly just go quickly into some of the clinical data here. I think it's important for people to remember that vaccines can induce immunity in different ways. There's something called protective immunity, and that relates to protection from severe disease. We've definitely seen that with these vaccines. No question, almost 100% of all of them will prevent severe disease, hospitalization, and death. Sterilizing immunity is what most people think about, which is that if I get the vaccine, I'm not going to get infected. We've got some very tantalizing evidence that that exists for these vaccines as well. It's not at the 100%, 99% we see with protective immunity, but it's probably around 70. And then ultimately, which would be really cool to ending the pandemic, is a really transmission immunity, which is really an offshoot of sterilizing immunity. If you can't get infected, you're not going to transmit the virus to somebody else. And again, some tantalizing evidence, I'm going to show it to you in a second, that transmission immunity is likely a result of some of these, if not many of these vaccines. This is a real crazy sciencey slide, but I actually put it on here so you can pay attention to the blue lines and the red lines. And Dr. Bernstein will have to forgive me if I put something here which makes it look a little bit simple. But one of the things I'll draw your attention to is the blue line is T cell responsiveness. So these are the cells in your body that don't make antibodies, but they orchestrate the immune response. And part of that orchestration is to create a memory response, which you can then leave a durability of immunity afterwards, and are responsible for some of the immune effects by attacking viral infected cells. We've spent a lot of time on the red line, which is the antibody response, which is mediated primarily by B cells. The immune system is very complex. There's a lot we know about it now, but it's important to remember there is a T cell response we see to many vaccines, including the vaccine for SARS-CoV-2. Here's the 4 vaccines that are currently licensed now in Canada for emergency use. The 2 mRNA vaccines, messenger RNA vaccines, and then these 2 ones which are non-replicating viral vectors. Typically, an adenovirus, AstraZeneca is a chimpanzee adenovirus. The Janssen one is a human adenovirus. Varying different schedules, which are really dependent on how they design the randomized controlled trials. So the Janssen one, they basically did a 1-dose trial. So the regulator said, yeah, we got data, so we'll do it for 1 dose. But there's no magic about this one. They could have easily just done a 2-dose regimen. So this is what people are scared about. They heard about Moderna and Pfizer. Wow, look at this efficacy. Oh, that's Johnson & Johnson. Well, that's not as good as this one, right? That's a lower number than this one. And you can see here that this is a lower one than this one. AstraZeneca did some really crazy stuff with their clinical trials, and I won't go there without explaining all the goofiness that went on. But essentially, the problem here is you can't look at this and say this is a better vaccine than this one. Why? Because very simply, when Pfizer and Moderna ran their trials, the number of cases of COVID, this is actually an American graph, the number of cases of COVID-19 was actually fairly low. But when AstraZeneca and Janssen were running their trials, you can see this huge upswing in cases. So that's going to dramatically influence the results you're seeing because they were done at different time points, and there was a different prevalence of the infection out there in the community amongst the subjects that were part of the trial. So be very careful not to compare efficacy. It's really, really not relevant. So when you look at these vaccines in general, and ignore the Russian vaccine down here, please, and Novavax, which is not yet approved. This is the protective immunity. This is what these vaccines did in preventing people from being hospitalized with COVID-19 or severe illness. Moderna, 97%. Pfizer, 100%. Johnson & Johnson, 100%. That's the Janssen one. 100% for AstraZeneca. That's what really is. We know these vaccines are enormously protective. When you look at their efficacy, I've already gone over those numbers there. Protection from severe disease, also extraordinarily high. This is amazing. These are vaccines, doesn't matter which one you get. If you get this vaccine, you're not going to die of COVID, essentially, based on what we've seen with these large randomized trials and with ongoing real-world evidence. Here's some real-world evidence. This is the UK. They rolled out the vaccine during January, and here you can see the deaths And then the vaccine effect here with the reduction in deaths. This is an amazing drop. I mean, it doesn't take a rocket scientist. Actually, it wouldn't take a rocket scientist. They know nothing about vaccines, by the way. They know everything about rockets. That this is a huge drop in the number of deaths and cases that pop up here. And then this is some really cool stuff, just came out in the last couple of days. This is vaccination at 2 medical centers of acute healthcare workers in the United States. This is a group from Texas. This is a study from California. And what you, no, sorry, I think so. I think this is the California one, that's the Texas one. Here's non-vaccinated employees. So some employees didn't take the vaccine. Some were partially vaccinated by 1 shot. And here's the ones that were fully vaccinated. Holy mackerel, that is an amazing response in terms of new SARS-CoV-2 infections arising in these particular groups. Here's the data from the California group. And you have to here to look at numbers. So this is dose 1, dose 2, and the number of days after. And look what happened. In the first 7 days after vaccine, yeah, they were still seeing some infections. Around day 8 to 14, they're starting to drop. Boy, after day 15, they're really dropping. And just before their second dose, they're really low. And then when you get your second dose, they're just about disappear. So these are amazing studies, real world effectiveness, not an experimental randomized controlled trial. This is vaccinating people out there in a country, the United States, which has lots and lots of cases. So it's really important to look at. I'm going to entice you with a very quick summary that was provided by one of my colleagues in San Francisco, Monica Gandhi, who put together this table looking at reduction in asymptomatic infections by testing. And what you can see here in England, in Israel, in Mayo Clinic, here's another bit from the Israeli studies, and here in a British study, this was a reduction actually in transmission of infection from vaccine recipients to someone else. Some of these are preprints, but some of them are already out there in the published literature to be peer reviewed. So this is the holy grail of vaccines, transmission immunity, where you're actually preventing transmission of the virus. Very quickly, because people always ask me about this, side effects after first and second dose. Here are the different vaccines color coded here. So you can see basically there's a little bit more reactivity of the second dose, but I would say principally you're seeing that with the mRNA vaccines. Dr. Bernstein and I can probably explain it to you, but it relates to the method of delivery. Interestingly, people who get the AstraZeneca Janssen vaccine tend to have more reactivity with the first dose and less with the second dose. If that means anything to you. These are mild effects. They're signs of immunogenicity. They're activating the immune system. So you get a sore arm, you get some swollen lymph nodes, a bit of fever, headache and fatigue, but they disappear very quickly. These are essentially pretty darn safe vaccines. This is always of interest. What about young people compared to old people? You see a little bit more sometimes in young people because they have a more responsive immune system early on in life. It starts to disappear when you're a little bit older. And so your side effects are a little bit less, but essentially that's what the side effect profile looks like. If you want to look at it in this diagram here, this is first dose. You can see most things are close to 0, but then as you get the second dose, again, most of the data we have is on Pfizer and Moderna, a little less on Janssen. The side effects are a little bit more so with the second dose. So if you've had your first dose and it's AstraZeneca, the second dose will probably be easier. If you got Pfizer, Moderna, it'll probably be a little bit rougher that the second time around. But remember, that's a short-term pain for long-term gain. So summing up, where are we now? We're in a third wave. We've got a lot of variants floating around Ontario now. Over 50% of our isolates now, positive tests are actually 501Y positive, so they're variants. They are a cause for concern because we're looking at an increase in transmissibility and virulence, but the vaccines we have are effective and safe. We've got more on the horizon, and Dr. Bernstein's nicely talked about sort of some of the issues around that sort of effect. In essence, I put this up here because we're in a minefield. We're here, and between us and this lovely summer meadow out that you can see a few hundred yards away, there's a few mines we have to avoid on our way over there. So I think it's a useful analogy to sort of put us where we are at the moment and why we have to continue to knuckle down with public health measures while we get all these vaccines into people, because they are, as Dr. Bernstein said, we're going to science our way out of this whole thing. And just a reminder, therefore, so get the vaccine, but keep doing all these good things here too, because they're going to help to control things as we walk through this little minefield that's there. So I'm going to stop at that point, and I'm going to stop sharing so you can see people, and happy to have John tell us where we're going from here.
Okay, well, thank you very, very much. All I can say is, wow, that's more science than I've read in the last year, and I read every story online, as Alan certainly knows. I'm going to start with my question first, which no one else has asked yet. There's a whole bunch of questions have been asked, and so we'll get there. Both of you referred to variants, and that is really the issue of the day, isn't it? As mistakes that happen during replication. I wonder if they're not mistakes but improvements. Is the virus actually encountering resistance in a body, then replicating in a different way so that it can keep on going? Therefore, it's an improvement, not a mistake. Just my thought.
So
I'll take go ahead, Alan, and I'm going to make a little comment about the American variants because that's pertinent to the question. But you go ahead first, Alan.
It's a great question, first of all, John. So I'll give you a 101 class in Darwinian evolution. All the mutations that happen are random. There's no a priori selection beforehand. And actually, most mutations are deleterious to any organism. Just by, if you make a mistake when you're copying someone's book, the odds are, instead of writing the horse, it might come out the house. But you don't want it to say that the house is jumping over the hedge. So most mutations are actually negative for that organism. Every once in a while, there will be a mutation which happens randomly that will be advantageous to the organism. So in the case of COVID, the B117 is a good example of that. That mutation seems to make as you heard beautifully from Gerald, makes the virus more transmissible, more infectious from person to person. That's obviously advantageous to the virus. It will spread more, make more virus. So it didn't plan that. It didn't design that. It happened by chance. But once it's happened, it gets what the expression is fixed in the viral population, and it spreads. And so that's what you see. Now, what's interesting is we didn't see, at least as far as I know, we didn't see these mutations like this. We'll just stick with the B117 for a moment, the N501Y. And you all know N is asparagine, Y is tyrosine, right? So we didn't see that mutation early on. Now, the odds of it happening early on per virus was no different than later. So one could argue from evolutionary theory that the fact that we've been washing our hands and wearing masks and keeping our distance is putting pressure on the virus, selection pressure, that if it wants to survive and transmit, it's got to become more infectious. And so I interpret the presence of that mutation and its selection later on in the pandemic as evidence that our traditional public health measures are actually working, that we're putting pressure on the virus to become more infectious. And ditto, the E484, the South African one, which is relatively resistant to the antibodies that are made when we are, you get the vaccine or infected, also suggests that the virus is having trouble encountering people who have do not have antibodies that can kill the virus. Because as more and more people get infected, there'll be more and more people who have already been immunized, in a sense, by natural infection. They'll have antibodies against the virus. So the virus will have trouble spreading. And of course, as more and more people get vaccinated, it'll also have trouble spreading. So we're getting at a situation where there's more and more selection pressure on this virus to escape the antibodies that are made when they're infected. So you're getting more evolutionary pressure for those South African mutations, the E484K mutation that we talked about. So if that does not happen, then the virus will die out. So that might be why SARS back in 2003 died out. Most of the mutations it sustained probably killed off the virus. We're not compatible with viability of the virus. So long answer to your short question, sorry.
But that was a great answer, thank you. Okay, so I'm gonna get to some of the ones from the
I
audience.
just want to, if I can just add on here, just something very important that's very American. And I do have a sister who lives in Connecticut. She's American citizen. She's married to an American. The Americans have done a wonderful job, actually, of selecting out particular mutations in the California and New York variants, which are resistant to the monoclonal antibodies, which they have used very extensively. Many of you may recall that the former inhabitant of the executive branch, the head of the executive branch in that country, got the monoclonal antibodies when he got sick. And the Americans have used a lot of them, very expensive. The only country in the world can afford them. They've actually selected out that these California and New York variants are resistant to those monoclonal antibodies. So that's an example of a direct pressure effect, evolutionary pressure, that obviously, if you were wiping out all the viruses, the random mutations that popped up that were resistant to the monoclonals are now really spreading and have created. So the Americans have done a wonderful job of creating variants which are resistant to the monoclonal antibody therapies that we were using early on in the pandemic.
It's a little bit like if you overuse antibiotics, you get antibiotic resistant bacteria.
If anyone could do it, it would be the Americans, no question. So question from Bert. I've been told that the spike is successful by engaging the ACE receptors. Some of us take ACE inhibitor medications, which block ACE receptors. Would these drugs make infection less likely with exposure to small numbers of viruses?
It's a great question. I haven't had that one since early in the pandemic. The answer is no. We know lots of studies of angiotensin receptor blocker agents like valsartan and others, and ACE inhibitors like lisinopril and perindopril and all those ones. Absolutely no difference. It does not increase the likelihood of you getting infection, and it doesn't create problems with you having a more severe form of it. That has been well answered with very good observational studies.
Great. A related question then from Dawn. Are there any common drugs we take that might interfere with the vaccines?
Not that I'm aware of at the moment.
No, not that I'm aware of either.
So that's all good news too. What about human immune systems? Are they all the same? Are there groups? Does gender matter? Does race matter? Has that been determined yet?
I get to throw in my favorite punchline. Women are superior to men genetically because they actually, our Y chromosome is an X chromosome with a piece of it missing. So women have more genetic material than humans. It's a joke, folks. But essentially, women do have a very robust immune system, which is why autoimmune diseases appear more frequently in them. And interesting, in SARS-CoV-2, men have a higher mortality rate after severe illness than women do. The infectiveness of both groups is exactly the same, though men and women can acquire this virus quite similarly, but women seem to have, for some reason that may be related to their genetic background, or do better with severe illness than men do.
Well, I think the other point about differences between people, just to add to what Gerald said, is as we age, our immune system gets less robust, it weakens. And so that's a big issue. And that's one reason why seniors, and especially frail seniors, are much more sensitive to most viruses, including this, or especially this one. And there are also more subtle differences between individuals in terms of the quality and the quantity of their immune system, but there's probably a second order effect relative to what we're talking about now.
Yeah, and one of the interesting thing is that remember I mentioned being protected from severe illness. That's probably literally not mediated by antibodies. That's mediated by T cell responsiveness. And that explains why you get this incredibly robust T cell response. Some of my colleagues, basic science colleagues, immunologists, have been studying this, and there are tremendous T cell responses to the infection, as particularly the vaccine. And vaccine immunity in this disease is probably better than natural immunity, dare I say that? But there's an emerging evidence of it. So in fact, when we look at these antibody levels, which is kind of what we look at and people are talking about it, and it's very true, Dr. Bernstein very carefully pointed out that antibody responses to generic vaccines are lower in older people and much more robust and higher in young people. But T cell responses are still pretty good. And that's actually what mediates protective immunity. And that's why these vaccines are incredibly effective, because they almost all universally, with that spike protein that they're giving you in a way, producing a tremendous T cell response.
Okay, let's come back to your story about the irresponsible students at your university, Dr. Evans. I'm sure Queen's is no different than any other university, as you noted. Should we perhaps then be vaccinating the young, more social people earlier? And this same sort of question has come up in people talking about we should be maybe vaccinating the workers of supermarkets and that kind of thing, where they're in more contact with people. What do you think?
Yeah, so if any of you get the Globe and Mail, probably many of you do, read the story that I was quoted in this morning about PEI's strategy to vaccinate 18 to 35-year-olds who work in grocery stores, gas stations, etc. They have the luxury of a small population, and they've now gone out with that strategy. I wholeheartedly agree. So when you're looking at the vaccine strategy you have really two essential goals you can go after. One is reducing the impactfulness of severe disease and death. And if you want to go that way, you vaccinate older people, as was Dr. Bernstein and I both mentioned, older age groups carry the brunt of this disease. If, however, you just want to reduce cases overall, you actually go after the group that tends to generate this. I can show you tons of social data. That is basically sort of older adolescents, young adults out to about age 30 to 35. And if you mass vaccinated them, you would have a dramatic reduction in case numbers. But we have all decided, and I think rightfully so, and I say this as a physician who has to take care of sick people, we've decided we really want to protect our older individuals in our society and people in congregate settings. And so our priority has been to get them protected. We know the vaccines are very effective at doing that. But if you're lucky like PEI and it was very quickly easy to vaccinate all the older people, then now you can start driving your vaccine towards reducing overall case numbers by going after the age groups, the age cohorts that tend to generate the infection. And they generate it because they socialize, they interact. Our interactions as older adults is nowhere near what it was when we were ages about 16 to 24. 16 to 24, you're basically trying to grab any human you can around you and socialize with them.
The only complication I would add to what Dr. Evans just said is, as he pointed out in his presentation, the B117 variant, the so-called UK variant, is more pathogenic, including more pathogenic in young people. And so it's making this sort of public health decision much more complicated, or ethical decision, if you will, much more complicated because of that.
Yeah, absolutely, Alan. Very good point.
So a question from Dawn, what about long COVID? And certainly we've all seen, I've seen lots of stories about what seems like significant number of people have lingering symptoms or changing different symptoms over months and months and months and months and months. What do we think is going to happen? Is this going to fade away, or are people going to have permanent damage as a result of getting this disease?
Yeah,
I think one of the interesting things about long COVID is there's one paper, and there may be more that you're familiar with, Dr. Evans, about people who have been vaccinated who have long COVID. A significant number of them seem to have ameliorate the symptoms, or the symptoms go away completely. So that was, and so one of the encouraging things about that, other than we're actually perhaps curing long COVID, is we don't really know why some people get long COVID disease. So the fact that vaccination might work to get rid of it suggests there might be low levels of virus in the tissue, still causing tissue damage. And the vaccination is yet another way of boosting the immune system. So it gets rid of the residual virus that's in our lungs, or in the brain, perhaps, or in our heart. So there might be a clue there that perhaps vaccines or drugs against the virus might also have some effect. But one of the mysterious things about it is we haven't understood the origins of long COVID disease.
Yeah, that last point is the one. We don't really know what causes long COVID. Let me tell you, as an infectious disease doctor who's been practicing for three decades, we know and have lots of evidence of many different infections that exist that leave people with persistent, prolonged symptoms, which are difficult to explain and understand from a pathophysiological or pathogenetic mechanism. But what Dr. Bernstein said is absolutely true. One of the clues with this one is that we are seeing an effect when you immunize these people with exactly what he said, amelioration of symptoms. So we're still studying these people. And there's a lot of groups now that have begun in earnest collecting these individuals, putting them through a thorough assessment, measuring a lot of different things that we can measure, like cytokine responses and immunologic responses, get a real feeling for which organ systems are affected. And what we're going to find, I'll tell you, is that this is a heterogeneous group. This is a group of people, some of who have long COVID symptoms because of persistent infection to some degree, maybe some that have an over immunologic response, much like you see with autoimmune diseases. And then we're going to see people where perhaps some tissue damage that was done that was unsuspected has sort of popped up. So what I'd say is stay tuned for long COVID. We're going to be studying this for years after the pandemic to figure out exactly what it is.
Okay, so Paul asks, will original vaccine recipients, that is those who've had the full course, need a booster or another shot at some point to battle the variants? And I guess the secondary part of that question is, does this mean we're likely going to end up needing an annual vaccine against this virus like we do for the flu?
Great question, actually. We had a long discussion about this, about 2 weeks ago now on the vaccine task force. Look, there's what you really want, of course, is a universal vaccine that would be effective against sort of coronavirus classic and all the variants that are popping up. We don't have that yet, but with the RNA vaccines, which are a huge breakthrough, of course, in vaccinology, it's fairly easy to alter the sequence of the RNA to accommodate some of the worst variants that we're coming across, including the South African one, the E484K variant. And so Moderna, in fact, has already started a clinical trial with a modified vaccine that is designed to deal with that variant. So we'll see what that trial shows. My guess is we'll have the results within a month or two, actually. And that we'll be able to then think about just what the questioner said, actually, which is just like we need an annual flu shot because the flu virus changes every year, we might need an annual coronavirus or COVID shot because the COVID is mutating every year. But I'm actually a little bit more optimistic than that. I think what's striking to me is we haven't seen a lot of different mutations in the spike protein. We've seen less than half a dozen that are affecting the transmissibility or the pathogenicity or the immune escape variants like the South African variant, which suggests that either we haven't been looking hard enough, although the Brits have done a fabulous job of sequencing a lot of these different viruses. But the other possibility is there just are not that many different mutations that are compatible with viability of the virus and allows it to escape our immune system or the vaccines. So it might be that the 484 is the worst we're going to come across. That's the maximally optimistic view, but I think there's reasons to be optimistic here. So it could be that the next generation of vaccines are all we need. And so my guess is that we'll be looking at least a 2021 model or 2022 new model car or new model vaccine we're going to have to take to deal with those variants. Yeah.
One of the other interesting things is, when I was a research fellow, I actually studied coronaviruses. I studied one called mouse hepatitis virus, which is completely harmless to humans, but boy, does it ever do in mice. One of the things about coronaviruses that we know, the human coronaviruses, there's many of them that cause the common cold. They go by all kinds of funny names, OC43, 229E, HKU1, etc. What we know about them is when you get infected with a coronavirus, a human coronavirus causing a cold, you get very good, long-lasting protective immunity so that the next time you get that virus, your illness is not going to be anywhere near severe. And most of these, by the way, occur early in childhood, between about ages 0 to 5. That's when you get most of these coronaviruses popping up. But sterilizing immunity that prevents you from getting that virus again, that same virus, HKU or OC43 or whatever, actually is fairly short-lived. It's only about 2 or 3 years. So if protective immunity occurs, and as Dr. Bernstein sort of alluding to the possibility of a kind of classic coronavirus vaccine, then that protective immunity may last for decades and decades, because that's what we see with the human coronaviruses. And so the necessity of a second vaccine, if all you're going to get from SARS-CoV-2 is a cold and you're not going to die from it, and it's not a lot of it circulating around the planet, because we've kind of controlled the pandemic, then that's going to have an influence on the necessity of subsequent vaccines in the future. So I always have pointed out to people that when I talk about coronaviruses, that there's a lot of coronavirus research out there. We know a hell of a lot about coronaviruses, especially human ones. And this SARS-CoV-2, in many ways, acts kind of like a virus which now is adapted to humans. and it behaves exactly like all of its buddies, all of its buddy coronaviruses. So lots to think about is in that both the answers that Dr. Bernstein and I gave you. So we really don't know at this point, and we can make some speculations and thoughts and keep our fingers crossed that we'll get the best case scenario.
So I guess the more general question along the same vein that somebody that I think Janice asked is, do we have any idea how long the vaccine protection will last?
Great question. If you want to know how long it lasts, we'll have to wait a long time, hopefully.
Thank you. Yeah, Dr. Bernstein nailed that one. It's like, well, can you give us a chance to sort of follow people for a little while and figure out how long it lasts? So, because you can't answer the question right now because we've only had vaccine in people for, going back to the randomized controlled trials back in the fall.
So that actually leads about last thing to a question that we received by email. This question goes, I have a friend who sadly is an anti-vax person. It brought up the question that most of us have in the back of our mind. Vaccines usually need to be test trial at least 5 years for safety. How can we mass vaccinate humanity with vaccines created in less than a year? Can we trust that these vaccines will not have any serious side effects, say 5 years down the road?
Great question.
Yeah. I mean, these mRNA vaccines are incredibly safe, at least in the short term from what we've seen. But again, the safety signal for a long time out really is going to require collecting data as things move along of the original trial recipients of people who've received the vaccine. And that's part and parcel of the data that we're collecting right now on people who are vaccinated, because we can go back and find out if other consequences occurred. Dr. Bernstein might want to make some comments about the safety of vaccines. This new mRNA technology is amazingly, the platform they're using is actually surprisingly very, very safe in my view, as a clinician sort of looking at the consequences. And we've looked at mRNA vaccines for things like rabies in the past before SARS-CoV-2 came along. Vaccines in general are a lot safer than I think sometimes the general public is influenced by people who have varying opinions on this issue. That's what makes it really, really complicated. Hopefully, people believe people like myself and Dr. Bernstein, who sort of have studied this kind of stuff all our lives. Me as a physician, because I take care of people and certainly have a strong proponent for people to get their vaccines. One of the things that strikes me about people who don't have confidence in vaccines is that they're kind of relying on everybody else to sort of step up to the plate and get vaccinated to get that sort of effective community immunity, if you want to call it, not herd immunity, since we're not all cows. That's where the challenge lies. And I'm actually sitting on a behavioral sciences working group here in Ontario, which is a working group of the science table that I'm at. And I'm working with these behavioral scientists because these guys are amazing. They really study a lot of what influences human behavior and human psychology. And hopefully there's going to be some stuff coming out of what we're dealing with and trying to get people vaccinated against COVID-19 that may help us in the future with really getting vaccine rates back up, because they've been done a great disservice by a lot of unfortunate things that have happened in the past with links that have now been completely proven not to exist, like the link of vaccines with autism, et cetera. So I don't know, Alan, if you want to throw your comments in there.
Yeah, I'll add 2 points, I think. One is, I think we're quite lucky here in Canada and in Ontario, including Ontario, that the rates of vaccine hesitancy, which is different than being an anti-vaxxer, but the rates of both anti-vaccine is about 10% in Canada. The rate of vaccine hesitancy is also very low. It's about 20% at most of people who are hesitating of getting a vaccine. So I think we're in very good shape. In France, for example, it's about 60% of vaccine hesitancy. And in the US, it's also much higher. It's 30 or 40%. That's the first thing. The other thing is the questioner started with, I think, a really important point, which is, given that these vaccines were approved so quickly, they went through the pipeline, as it were, so quickly, did we cut corners? And one of the corners being safety. And the answer is no. What we cut was red tape. And so normally when a vaccine is developed, the vaccine developer will do things sequentially: a phase 1 trial on a small number of people, then a phase 2, then a phase 3, and then they'll go to the regulator, in our case, Health Canada. In the US, it's the FDA, and say, here's our data. What do you think? And then the regulator will say yes or no, or we'd like to see some more experiments done, or we'd like some clarity on blah, blah, blah. And they'll go back and forth sometimes for a year. And then if it's finally approved, the manufacturer will then start manufacturing. What's happened with COVID because of the emergency is the phase 1 trial was done. Once the phase 1 was done, the 2/3 was compressed into one large trial. So there was typically 30 to 60,000 people. And that trial looked at safety and efficacy in a heck of a lot of people. At the same time, the data as it was coming in was being shown to the regulators. So it was done in transit, as it were, not at the end of the trial. So that speeded it up. Also at the same time, every country, including Canada, was signing advance purchase agreements. So we signed an agreement based on the recommendations from the task force I'm on with Moderna, Pfizer, all the other vaccine manufacturers that we know about. So the manufacturers received money up front so they could start making vaccines, whether they knew they would be effective and safe, and whether they knew they would be approved or not. They were at-risk investments, as was the phrase. So that would speed up a heck of a lot of time at the end when Health Canada, in our case, approved the vaccine. There already were vaccines ready to go. So we didn't cut corners, we cut red tape, and we did things in parallel, not sequentially. So in terms of the safety of these vaccines, they're as safe as any vaccine that's ever been made. One reason we know about all the problems with the AstraZeneca vaccine, for example, is there never has been a vaccine being made that's been under the microscope so much by so many people. All of us are reading about it on the first page of our newspapers. Well, normally you don't read about adverse events in a trial on the first page of a newspaper. You never read about it. Health Canada gets the data and then they decide what to do. And then one day your doctor says, there's a new vaccine for shingles. You should take it. You never hear about any of the, all the things that can go wrong on a trial or scaling up or manufacturing. And so, we're having a sort of a global immunology class here because everybody in the world is following this and a vaccinology class. It's really quite remarkable as a scientist. I just love it that everyone's learning about T cells and antibodies and, blah, blah, blah. So we have to remember that these trials are under a microscope. And the fact that we're catching every time somebody gets seriously ill, as happened with the AstraZeneca vaccine, or sneezes, the whole world knows immediately, which I think speaks to how well these vaccines are being regulated.
Great answer. I have several folks have asked a related question, and that's around the delay process in getting the second dose of the 2-dose vaccines. We all know the manufacturers have recommended a rather short time frame, 2 to 3 weeks, and various governments are stretching that out. And in fact, we're looking at 8 weeks in some cases. What are your feelings on the impact that has ultimately on the immunity that's provided by the vaccines?
Well, Gerald, do you want to take this or should I take it first?
I'm happy to sort of step in because I've got my answers all set up there. The construct of the short periods for Moderna and Pfizer were a construct of the randomized control trial. They had to get the trial done quickly so that they could get results on efficacy out there and some safety data quickly. Normally, vaccines, oftentimes when they're administered as a first and second shot, are separated by anywhere from 3 to 6 months because the initial shot creates the effector response in the B cells and T cells. And what you're looking with the second shot to do is to increase the durability of that response by representing the antigen, the vaccine itself, to the immune system so that it amplifies the memory response, which keeps that nice immunity going for a long, long time. When a regulator like Health Canada looks at trial data, they approve it based on how the trial was done. In the case of Pfizer, 3 weeks between 1 and 2. In Moderna, 28 days or 4 weeks between 1 and 2. So they have to go with that because that's the data they were presented. But And immunologists will tell you that's not ideal, because one of the problems you have is if you give a second booster shot too close to the initial booster shot, all you get is an increase in the effector response, and you don't amplify that memory response, which is required for the durability of the immune response that you're trying to keep in somebody. So it goes to this issue that someone asked about, how long is the protection there? So when we modeled it, and this was the other part of the equation, when we modeled it, we found that when we gave more people the vaccine by going to first doses rather than hoarding vaccine for second doses, we got a tremendously better effect on reducing case numbers. And we knew that we were still going to get protection from first doses, even in elderly people, for a period up to about 60 to 90 days, when you look at the sort of neutralizing antibody responses dropping. So in a way, we have to be very careful that it's not that the manufacturer recommended it. That's just the way they designed their trial. And that's the way the regulator looked at it and had to approve it, because that was the evidence that they were given. You know, second shots are probably reasonable out to 3 to 4 months, particularly the younger you are. And the only group that we're still looking at is very elderly people over 80, looking at some people with some immune conditions, not all, but some conditions that reduce immunity, because we know that their response to the first dose, as measured by antibody responses, is a little bit lower than what we would see in younger, healthier people. And that's the sort of unanswered question. So we're trying to find the right medium for when that second dose might be given, a little bit closer to what it was designed in the trials, because we're dealing with a very old person or a person with a lot of immune problems that specifically relate to vaccine responsiveness. But if you look at most healthy younger people, separating the dose up to 3 to 4 months is not going to make a difference, and in fact will likely increase the durability of the immune response that they get from the vaccine.
Okay, here's a triple-barreled question, kind of related. What do we need to do in terms of vaccines and public health measures to protect against the next virus? As if this one wasn't bad enough, but we do know there's probably more coming. What do we need to do? Does Canada need its own vaccine industry? And what happened to Quinte Labs anyway?
All right, I'll take this one. Well, I think I've read in a column that we need our own domestic manufacturing capacity, and we used to have a couple of generations ago pretty good vaccine manufacturing. We lost it by and large, not completely, but we lost a lot of it because of the consolidation of the pharmaceutical industry around head offices in the US and France, Switzerland, and England and Sweden. And we don't have head offices here in Canada. And I think we're paying the price now in terms of relying on other countries and their willingness to export, of course, to us. So I think one of the lessons from this pandemic is we definitely need to rectify that, and the task force has been looking into making recommendations to the federal government on that point, and I hope that we'll see something in the federal budget next month. I guess it's next month to that effect, but we'll see whether they listen to us. I think the other point is. I think one of the other lessons is how important it is that we collaborate and have robust multilateral institutions that will make sure we don't have this fist fight that's going on right now, where the EU is saying that they're not going to export any vaccines. President Biden is forbidding any exports of any vaccines from the US. The result of all that is, of course, the bulk of the world is not being vaccinated. Most people in the world, if you think about Southeast Asia, if you think about Africa, if you think about most of South America, is not being vaccinated. And as you know, it's almost trite to say now, but if no one is safe unless everyone is safe. And the proof of that, of course, is just look at how quickly the virus came from Wuhan to Canada, or the variants came from South Africa to Canada, or from UK to Canada. So we're kind of kidding ourselves if we think if we immunize ourselves, we're going to be protected, even if the rest of the world isn't. Because the only way where that's going to happen is if we stop all trade, stop all travel, nobody can come in, nobody can leave, nobody can come back. That's never going to happen, and it's not going to be a lifestyle that any of us would accept in the long term. So we need robust multilateral processes that will share the science and the riches of our science with the whole world as quickly as possible. And and the Wellcome Trust and the Gates Foundation both set up and the WHO a facility is called COVAX, which is for COVID vaccine. It's basically a bank account where countries can put money into it to buy vaccines for the developing world. So Canada, for example, has put in close to $500 million into COVAX to buy vaccines, half for us and half for the developing world. And we've been criticized because we said, okay, we want to take that 250 million and use it to buy vaccines for us. It could be used to buy vaccines for the developing world. So, and the US was not buying into COVAX while President Trump was the president. President Biden, I think, has reversed that now. But we still don't have enough money or production capacity in the world, even if there was enough money in that bank account, to produce enough vaccines fast enough to vaccinate the whole planet. So, if you think about it, this is a humongous operation. There's 8 billion people roughly on the planet, 2 doses per person. That's 16 billion shots that have to be administered. That is just an effort that we've never seen before. And it's not just who puts the needle in your arm, it's 16 billion needles that are required. It's roughly 1 billion or 2 billion vials, glass vials with rubber stoppers that are all made properly and sterile. It's an effort that we've never seen before. It surpasses what happened in World War II, turning out jet fighters, turning out the fighter planes. So this is a huge effort. So I think for the next pandemic, we need to make sure that we have these multilateral approaches, that we're ready. We also need to make sure, of course, that we have a radar system, that we're actually detecting abnormal events faster than they were detected this time. And there's something that we didn't do well and that we did do well. We let our early warning system within the Public Health Agency of Canada, the group of scientists, that was allowed to let go. And so we missed that early warning system here in Canada. On the other hand, there's a small company in Toronto called Blue Dot. Blue Dot is an AI-based company that was the first company or the first group to detect something funny going on in Wuhan, because they saw abnormalities in the patterns of telephone calls and travel in and out of Wuhan using artificial intelligence. And they immediately alerted every one of their clients that there was something funny going on in Wuhan. It's quite a remarkable story, actually. But they didn't alert governments. Governments were not a client of this small company. And so we lost a precious few weeks. Now, whether we would have acted as quickly if we had known that a few weeks earlier is a moot point, of course. So I think the lessons are, just to sum up, we need more manufacturing capacity, not just the vaccines, but the whole supply chains of the thousands of chemicals, the vials, the vaccines, all that kind of stuff, both here in Canada and elsewhere. We need more multilateral approaches. We need to help each other if we want to help ourselves. And it's the right thing to do, after all. And we need early detection systems that are more effective than what we have now. And we know we can do them. We have the technologies.
I do have to shove off. My wife is probably given up trying to keep what dinner I might have at home, although I probably don't need it. I would say one little thing, because Dr. Bernstein did a beautiful job explaining a lot of stuff.
No, you did the job.
I think you have to fundamentally understand something about public health. And this is something I'd like to leave everybody with. When public health is effective and does its job, nothing happens.
Right.
Okay. And we're very used in our society to, when you do something, then something happens. But if public health works well, and that's why we have to keep our investments there, nothing happens. So that's my little sign off at that point. So.
Well, thank you so much, Dr. Evans. I hope your supper isn't too cold. And we'll see if the remaining questions can be handled by Alan. I'm sure they can. So
I won't be able to do nearly half as good a job. I'll call you if I have to. What's your email address, Gerald?
Exactly. Anyways, thank you very much. And thank you for the invite. I hope it was informative.
Super.
Cheers, all.
Okay, moving on to autoimmune diseases. There are two questions. One person asks, will these vaccines cause autoimmune disease problems like psoriasis to become worse? And the other question, just generally, will the vaccine affect those with autoimmune diseases?
So I would say in general, autoimmune disease should not be an issue with most vaccines. We're all familiar with what happened with the AstraZeneca vaccine, at least in a few countries in Europe. So I would say if you have a serious autoimmune disease, you should first go to your doctor and get his or her advice about whether you should take any of these vaccines, any vaccine actually, but including the AstraZeneca vaccine or any of the COVID-19 vaccines. So I think and it's still not clear whether the AstraZeneca vaccine is really causing these disorders, the deep vein thrombosis, which may or may not be related to an autoimmune disorder. So there's a lot of confusion there, but to be on the safe side, which I think one should be, you should talk to your doctor about it first.
Okay, good advice. Someone asks, if you've had a COVID infection and subsequently got the vaccine, is there an effect on vaccine efficiency? Is there a need for the second dose? Are there any risks to the second dose, for example, T cell sequestration? And not quite related, but what happened to the flu?
Well, on that latter point, just to answer that one, this has been almost a non-existent flu year. And now we can't do the experiment of whether it was just a mild flu season because we have mild flu seasons, or whether it was because we really were observing our traditional public health prevention, toolboxes, wearing a mask, physical distancing, and washing our hands, all of which will prevent any virus from spreading, including the influenza virus. So I think we can assume that the reason it's been such a great flu season, that is an almost non-existent one, is because we were protecting ourselves against a different virus. So yeah. Now, the first question was about, I just blanked out. Remind me again, John, what was it?
Someone who's had COVID.
Yes, okay, yeah.
Gotten the vaccine, and should they get a second dose?
Yeah. So there is some evidence that if being naturally infected with COVID is essentially like getting the vaccine. Your body sees the virus and treats it like, it's an immunogen, as I explained at the beginning. It's like getting the vaccine. And so when you first get the first shot of the COVID, of the vaccine, it's like your body's now exposed to that antigen the second time. So you're getting a booster when you get the first shot of the vaccine. And so if you look at the levels of the immune response in somebody who's been infected naturally with the virus, and then they get their first dose, it's as if they're getting their second dose of the vaccine, so which is great. Now, the second part of that question was, is it harmful to get a second dose? The answer is no, it's not harmful.
Okay, good. A timing question. We've talked about the vaccines, continuing to develop the vaccines to handle the new variants. Do we have any time frame thoughts as to when such a booster or a variant vaccine will be available?
My guess is that the Moderna vaccine, the sort of the 2021 model, will be available in the fall.
Okay.
So just to expand on that a little bit, it's very easy to modify the RNA vaccines, as I said earlier. You can alter the sequence of the RNA to accommodate that 484 mutation, for example. Then you have to test that the single change in one letter of the spike gene has not made the vaccine unsafe or not made it harmful, and it's still effective. Now, you don't have to do a complete phase 3 trial. All you have to do is show it's safe, which means immunizing a certain number of people. I'm not sure what the regulators will require, but let's say 100 or 200 volunteers, and following them and then measuring the immune response in those volunteers, 100 or 200 volunteers, and see whether the antibodies that they make will neutralize, will kill the South African variant. And so all that can be done quickly. And then there's the manufacturing of the vaccine. So if you add all that up, it takes you into the fall. So I think we can expect to see the next generation of vaccines coming in by the fall, roughly.
So perhaps related, when do you expect we'll be able to vaccinate those for whom the current vaccines are not recommended? So children, the disabled, and so on.
With children, which I can answer more definitively, the trials have already started of looking at safety in kids, and so that will happen pretty quickly. Now you can appreciate the manufacturers want to go very carefully. They don't want to expose kids to a harmful, drug, as it were. And so they're doing these trials in sort of 2-year intervals, taking younger and younger children to see whether indeed the vaccines are safe. But we won't be safe as a society until everybody is vaccinated that is able to and wants to get vaccinated. So I think that will happen over the next few months, that we'll start to see a safety profile for these vaccines, especially the RNA vaccines and then the viral vector vaccines. We know that the tried and true technology, which is not yet on the market, is the protein subunits. So that's where we don't take the RNA or the DNA or the gene for the spike protein. We actually take the spike protein itself. We purify the spike protein. That's the Novavax vaccine. It's slower to manufacture, it's slower to test, and that's why it's not on the market yet. But in the trials that have been done so far, it is remarkably effective and protective against COVID-19. That vaccine, that we already have vaccines on the market that are safe for children, obviously with a different protein than the spike protein, but the technology has been shown to be safe with children. The RNA vaccines have not been shown to be safe with children yet because it's a whole new technology. So I think once the Novavax vaccine is approved, I think we can expect it to be used on children pretty quickly, actually, for that reason.
Okay, a question about mixing and matching the vaccines, and I'm going to extend that to another question, because that's been popularly asked. Can you take one vaccine for the first shot and another for the second? Or perhaps getting an annual booster shot would maybe be okay, taking a different brand of vaccine. And the extension of that would be, will we end up at some point with a single vaccine, like we do for the flu, that everybody on the continent at least takes the same one each year, and it's developed for that year for the purpose?
Yeah. So we have a kind of a unique situation with COVID-19. We have a smorgasbord. We have a sort of a Chinese menu of choose what you want off the menu. Do you want an RNA vaccine from Moderna? Do you want an RNA vaccine from Pfizer? Do you want a protein subunit vaccine from Novavax? Or would you like a viral vector from Johnson & Johnson or from AstraZeneca? It's a completely new situation for us. And so the opportunity of mixing and matching, or what's called a heterologous prime boost in the business, is now possible. And there actually are reasons, and I've said this in the media, for thinking that might be ideal, actually. The reason is the RNA vaccines, and Dr. Evans kind of introduced the idea that we have two major arms of our immune system. We have one arm that makes the antibodies, and another arm that makes these T cells, these memory cells that have various functions. So think of them as the Army and the Navy, if you will. So the RNA vaccines tend to activate antibody production preferentially, so that they activate the Army, let's say, whereas the other vaccines tend to be a little bit more balanced, so they also activate T cells as well as our antibodies. So they activate the Air Force. And so if you come in with one and then boost with the same one, you're preferentially activating only one branch of your defense forces, the Army. But if you do a mix and match with two different vaccines, you'll activate the Army and then you'll activate the Navy. And so you get a more robust immune response that way, especially if there's variants around, which there are now, of course. So there are some theoretical reasons for thinking that would be ideal, but we haven't done the trial yet, actually, to see whether that is indeed the case. And there's been talk both in the UK and here in Canada for doing that trial over the next month or so.
Okay. Kind of a general question, leaving aside COVID, has social distancing improved our health? Should we continue to wear masks? Certainly some countries we've seen for years, folks wear masks at certain times of the year anyway. And there's seems to be almost no flu. Is that a coincidence, or are we actually healthier by being apart?
Well, by being apart, we certainly haven't improved, I think, our mental health. I think there's lots of data that says mental health has suffered quite considerably by the social isolation that this has brought about, especially for certain groups. I would include teenagers and seniors in long-term care facilities, for example. So whether it'll improve our health is a good question. You know, there's a school of thought, especially around young kids, that they're best exposed to as many different foreign antigens or immunogens early in life to train their immune system for later on, as opposed to living in a sterile environment when they're younger. And I think there's good reason for thinking that's probably true. So I would say for young kids especially, no, it's not a good strategy for having a robust immune system. If you don't use it, you lose it, as it were. And so I think that's not a good strategy. For older adults who are perhaps prone to getting very seriously ill by being infected with influenza virus, for frail seniors, yeah, there is a logic, if you will, based on our knowledge of the immune system, for wearing masks and washing our hands and keeping distance. So that older people don't get infected with the flu virus, especially if it's a bad season for flu.
Good. And finally, because we seem to have come to the end of a whole lot of questions here, I'm not sure if this is political commentary or a real question, but I'll do it anyway. When Boris Johnson and the Swedish health authorities decided early on that herd immunity was a good idea to go for, didn't they get blowback about the danger of mutations taking that route then? Or did nobody understand anything about mutations early on?
Well, I'm not sure I understand the middle part of that question, John. So I didn't quite catch that, the middle part.
I guess the thought was that Boris Johnson made comments about potentially trying herd immunity. And Sweden actually really did take
Oh,
that.
yes, right. So early on, in the absence of a vaccine, Sweden decided, I think incorrectly, that if everybody got infected, there would be herd immunity. They would all have antibodies to the virus, or their immune system would be activated, and they would all be protected. The fallacy in that argument is that the assumption was that COVID-19 is a pretty benign disease. It's not. It's a very serious disease. You do not want to get COVID-19. And that's certainly true now, even for younger people, but it's always been true for older people. And look how many people we've lost in our seniors' residences here in Ontario over the last year. It's in the tens of thousands because of that. So you know, if you're willing to accept and sacrifice a whole generation of old people to achieve herd immunity, sure, go ahead, but it's not exactly the right strategy, I would argue. So I think the right strategy is what we've been doing, which is to keep our distance, wear masks, wash our hands, and develop a vaccine as fast as we possibly can, which is what we've done. I'm not a big fan. I think the herd immunity idea itself is a red herring. Because the people who push herd immunity will argue that we need 70 to 80% of people to be infected and have antibodies to achieve herd immunity. Well, 70 to 80% is basically 100%. So what you're basically saying is, to achieve herd immunity, we want the whole population to be infected with this virus. I'm not sure that's any kind of reasonable strategy for dealing with an infectious agent that's quite a serious disease. And you don't know, even with young people from the beginning, some young people have gotten very seriously ill from this virus. So now the debate in the field has been, okay, now that we have vaccines, what proportion of the population do we need infected, immunized to protect against this virus, to reach herd immunity? My answer again is, I don't think that's a relevant number. I think the relevant number is how many people can we possibly immunize as quickly as possible? Because that's really what we want to achieve. And if you subtract the anti-vaxxers and some vaccine hesitancy and our limitations, if we reach 70, 80% immunized, those 70, 80%, given how good our vaccines are, will be protected. That's all I care about.
Good. One final question, which is not really a medical one, but the thought that variants are moving around the world on international flights. Is there no screening before boarding? Well, yes, there is temperature screening, which is quite useless. People have to get a test generally within 3 days of their flight. Also useless because they can pick up the virus in between that test and when they got on the plane. And they may not have symptoms on the plane, and yet they're bringing the virus with them. I think that's a fair statement, is it not?
Yes, it is. And that's why we need to have everybody vaccinated as soon as possible.
So I think that's it, Lori. Also in the chat box are dozens and dozens of congratulations and thanks and praise for the presentations, just so you know, Alan. And this has been a fantastic session, so you can send us off, Lori.
Wonderful. Well, thank you so much, John, for your wonderful hosting and managing all those many questions. And Dr. Bernstein, thank you so much for answering so many of our questions and making it so much clearer, some of the questions that we all did have. Great presentation. I really, really appreciated your time, and Dr. Evans as well.
Dr. Evans did the heavy lifting.
Oh, well, you both, it was lovely. And I learned a lot, and I thought I had kept up, but I still learned more. So it was really, really informative, and I hope people took a lot from it. And I just want to say to everyone that we did record the session. I will, as I am able, to upload it, and then I will send out the link to everyone by email in case you want to refer to it. And some of the people that registered weren't able to make it to the meeting, so they can still see it. And just to let you know that we have an upcoming next speaker series on April the 28th. It's going to be on the importance of water. Suggested title is Precious and Free Water is a Vital Need and a Basic Commodity in a World of Climate Emergency. And our speakers will be Brad McNevin and Jane Leslie. So it should be a very good session as well. So hopefully, if you're interested in learning more about water in this area, feel free to join us at the end of April. And once again, Dr. Bernstein, thank you so much. You, Dr. Evans, did just a terrific job. Can't thank you enough.
Thank you.
Thank you, everyone, for coming. I really have a great night.
Thanks for putting this on.
No
Stay
problem.
safe, everybody.
Take care.
Okay, that's great.
Bye, everyone.
You gone there, Lori, already?
Yeah, I have a call from my uncle, and
Hold on, I gotta turn up my volume here. Sorry, there we go. I got you.
Oh, I just want to say I have to go because